but I'll remind some of the definitions. So Okada used this term Mori-Fano variety, which just means a Mori fiber space, which is a Fano variety, meaning a Fano variety which has terminal singularities, which is Q-factorial, and has Picard number 1. Then I'll remind that a Mori-Fano variety is birationally rigid if it is the only Mori fiber space in its birational class, up to isomorphisms. And the question I'm thinking of is, what happens to birational rigidity of Mori-Fano varieties when we add singularities? So this is a very natural question, because if we really want to think of MMP and the Mori category, we have to understand singularities and birational behavior with singularities. I will consider sextic double solids. So this means double covers of P3 branched along a sextic surface. Or an alternative description is a weighted homogeneous degree 6 hypersurface inside the weighted projective space P11113. And why do I look at these is that among smooth Fano threefolds, these have the least degree, namely 2. So we expect them to behave very rigidly in this sense, birationally. So what we know from before, a smooth sextic double solid is superrigid by Skovskik. If we add an ordinary double point, it's still superrigid by Buklikov. And then Cheltsov and Park showed if you add ordinary double points, as long as the variety sextic double solid stays Q-factorial, it's still superrigid. So yeah, this covers the case with ordinary double points. On sextic double solids, if we look at terminal singularities, the next simplest one, more complicated one, is to consider compound AN singularities. So a compound AN singularity means if you take the general hyperplane section, then you get the AN singularity, the Duval surface singularity. And Reed showed that these are terminal if they are isolated. I will show a local analytic form for such singularities. So first, let's define the weight of either a polynomial or a convergent power series. And this is just the least degree that appears among monomials in F. So that's the weight of a power series. And then from the definition, it quickly follows that a CAN singularity can be locally analytically given by x1, x2 plus h of x3, x4 inside the space C4. And here h has to have weight n+1. And then it's a CAN singularity. So I'll state my first theorem, which is describing sextic double solids with a CAN singularity. So if a sextic double solid has an isolated CAN singularity, then n is at most 8. And then for every n at most 8, a general sextic double solid with a CAN singularity has only one singular point, meaning it's smooth outside the CAN point. And if we look at a very general one, then it is a Mori fiber space, meaning it's Q factorial and has Picard number 1, except for one family. This one family does not have any Q factorial members. So I use the words general and very general here. So this means I constructed a parameter space for all sextic double solids with a CAN singularity. And then general just means it's in a Zariski open-dense subset of this parameter space. And very general outside of countable union of the proper Zariski closed subsets. Since it's a parameter space, we can ask what's the dimension. So we have, for example, sextic double solids with a CI1 singularity. I have a 77-dimensional parameter space. For CI2, 74, etc. So I'll say, yeah. So for all of these, N, there's exactly one family except for CI7. So this has 4 families, 4 disconnected components, and exactly one of them does not have Q factorial members. So how do we prove this? So let's start from a sextic double solid given by a weighted homogeneous degree 6 polynomial inside the weighted projective space P11113. And let's assume it has a CAN singularity at P. So this means we can locally analytically transform it to this form. x1, x2 times h, x3, x4. And yeah, h here is a convergent power series of weight n plus 1. So yeah, P is a CAN point. That means weight is n plus 1. This is the same as asking that all of the homogeneous degree I parts, where I is at most n, that these are 0. And this is the same as asking that all of the coefficients of these HIs, where I is at most n, are 0. So for every HI, every homogeneous part of H, we have exactly I plus 1 monomials, and we're asking that the coefficient of that monomial is 0. So we get a lot of conditions. So how do we get the parameter space is we express these coefficients of H, we express them as polynomials in the coefficients of F. So F is this degree 6 homogeneous polynomial. So yeah, at first it might not be clear that these are even polynomials, yeah, but they are. And it might not seem easy to compute it. So yeah, I found some algorithms to compute it in some specific cases, but I couldn't find an algorithm. So I couldn't find a computer algebra system that does it for me with general coefficients. So I wrote my own program to compute these coefficients. So this is algorithmic. Yeah, and works in general. So after we have found these coefficients, so let's look at the dimensions for a moment. So with CA1, we have a 77-dimensional family. To get the parameter space for CA2, we ask H2 to be 0. H2 has 3 coefficients, so this means we see that the parameter space dimension drops by 3. If we go to CA3, we ask H3 to be 0, which has 4 coefficients. So parameter space dimension drops by 4, and so on. So we see that these conditions, these algebraic conditions, are all algebraically independent. So we have a big simultaneous system of nonlinear equations of high degrees in 77 variables. Yeah, this might seem a bit scary, but actually there's a nice way to solve it. And then we get the parameter space. So the other thing to prove is that the general member is a very general member is a Mori fiber space. And for this, I use dimension counting. So, for example, let's first consider showing that it's smooth outside the CAN point. So, yeah, I use dimension counting for this, and the arguments, it seemed like very sharp dimension counting, because if I tried to show that for CA9, try to prove that it's smooth outside that point, then I failed, and this proof led me to a curve of singularities through that point. Yeah. One thing I'll say is that to prove that it's smooth outside the point P, normally, let's say for an ordinary double point, one would use Bertini's theorem, but here you cannot use Bertini's theorem because you don't have a linear system. Everything is very nonlinear here. Okay, I also looked at other singularities. So I constructed a sextic double solid with a CA11 singularity, and necessarily this is non-isolated. And then I also considered how many CAN singularities can we put on the sextic double solid. So this is an argument following a paper of Ahmadinejad Kalogiras. We look at the local Milnor number of an isolated CAN singularity, and it's not difficult to show that it is at least n squared. And then some arguments show that the total Milnor number of a Mori fiber space sextic double solid is 104, at most 104. So putting these two things together, a Mori fiber space sextic double solid has up to 1 CAN singularity or up to 2 CA7 singularities, etc., up to 26 CA2 singularities, or up to 104 ordinary double points. So we immediately see that this bound is weak because it is known that the sextic double solid can only have up to 65 singular points. So one thing I was thinking about is maybe this example with 65 singular points, Barth's sextic, maybe it is somehow unique or special, that maybe it is the most singular. So what does most singular mean? For example, in terms of the total Milnor number or the total Turina number. Total Turina number. But it turned out this is not the case. So answer no, because I constructed a Sextic double solid with total Milnor number 121 and total Turina number of 66. So yeah, I have no other idea how to nicely bound this number of singularities. So probably it's a very difficult question and depends on the type of CAN singularities you put on the space. Because, for example, for ordinary double points, it was the work of many people to prove this bound 65, and it was not easy. So I don't expect, for CAN singularities, it's probably more difficult. So now I will give my main theorem, which is that a general Murray fiber space Sextic double solid with a CAN singularity where n is at least 4 is birationally non-rigid. This, again, we have the word general here. That means, in this case, I have explicit, nice generality conditions which depend on n. And the proof is by considering each family separately, each of the 7 families I have, and constructing a Sarkisov link, which is different for every family. And this is the table that I get of the birational models. So let's say if we start from a CA4 singularity on a Sextic double solid, then we get an index 1, codimension 2, complete intersection. So this is found by Okada already, where he started from the quasi-smooth variety. Then if we start from a CA5 singularity, we get the link to another Sextic double solid. And if X is general, then these are not isomorphic. So then being not isomorphic, I proved it by showing that these singularities, these CA5 singularities, in fact, are not isomorphic if X is general. For CA6, we have a link to a hypersurface with a CA3. Then we have these 3 families of CA7. First one goes to a complete intersection, degrees 3 and 4, inside P 111122. And this one has, so the final step of the link in that case is a divisorial contraction to this ordinary double point. But in fact, this variety Z has 3 ordinary double points and 2 quotient singularities, if X is general. But if X is not general, it might have some other singularities. In the second family, we get the Sarkisov link to Z degrees 2, 4 inside P 111112. And this one has just one singularity, which is the CA2 singularity. And I mark this singularity here because that's the center of the last divisorial contraction. For the third family, we finally get something non-solid. So we get a Delpezzo fibration. And for CI8, we get the complete intersection with a CD4 singularity. So I am also waiting for this Hayakawa's paper to be published on divisorial contractions to CD and CE singularities. But, yeah, the divisorial contraction that I found is one of those divisorial contractions described by Hayakawa, but yeah, in some different local coordinates. And yeah. So next I'll talk about this. So if we want to construct a Sarkisov link, the first step is constructing a divisorial contraction from the Fano variety. And for me, I'll construct divisorial contractions where the center is the CA endpoint. Kawakita described these locally analytically, but it is not immediately clear what's the best way to construct them globally. And yeah, I'll give some nice conditions how you can see whether your morphism is this Kawakita divisorial contraction described by Kawakita. But yeah, before I do that, I'll have to give some define weighted blowups, in which way I use them. And yeah, this is weighted blowups. That's a known thing. So it might be a bit simple to some, but a bit later I'll have some nice constructions how to use this. So first we'll say, what does it mean for two birational morphisms to be equivalent? So if phi is a birational morphism from y to x, phi prime is a birational morphism from y prime to x prime. And then we say that these are equivalent if there are isomorphisms from x to x prime and from y to y prime, such that we have this commutative diagram. So in the case where x is in fact equal to x prime, then this equivalence of these two morphisms is just the existence of a birational, just the existence of an isomorphism over y, over x. So yeah. And then we say these two morphisms are locally equivalent if we can choose open subsets around the centers and the exceptional loci, such that when we restrict, we get equivalent morphisms. And we have analogous definitions for complex analytic spaces. In that case, these, instead of birational morphisms, we have bimeromorphic holomorphisms.
Eric, sorry,
yes.
Do you actually require that y and y prime be biregular?
Yes.
So if you have, for example, a birational involution on x, is phi and phi prime not equivalent?
So birational involution on x?
Yeah, centered on the same point.
Yeah, so you mean if this one is not an isomorphism?
No, that is an isomorphism, but y to y prime is just a birational map.
Yeah, so I want the y to y prime also to be an isomorphism. So, yeah.
Okay.
It could be that, yeah, if it's a local, if it's maybe not isomorphism globally, then it could still be a local isomorphism.
Okay.
Okay. So, and now we define a weighted blowup. So, yeah, this is known. So let W be positive integer weights w1 to wn, and let m be their least common multiple. Then we define the weighted blowup of affine space to be the geometric quotient Cn plus 1. We take away the 0 set given by x1, comma, up to xn, and we take a quotient by C star. This C star action is given by -1, w1 up to wn. So this means that lambda, where lambda is a non-zero complex number, lambda times u x1 to xn goes to lambda to the -1. So this -1 is here. And then lambda to w1 times x up to lambda to the wn times xn. So yeah, the weighted blowup is this geometric quotient. And this is the same, is isomorphic to the toric variety, which has rays, whose fan has rays E1 up to En and W. So here EIs are the coordinate vectors. So E1, for example, is 1, 0, ... 0. So we don't want only the weighted blowup of the affine space, we also want to consider the blowup of some subvarieties of affine space. So the weighted blowup of x prime inside Cn. So this is just, we take the weighted blowup of the affine space and we restrict it to y prime, which is the strict transform of x prime. And in general, we want to look at weighted blowups of any variety x. And this is just a birational morphism, which is locally equivalent to this morphism from y prime to x prime. I'll give a remark first that this weighted blowup really depends on this local isomorphism. So local isomorphism, this is this map from x to x prime. And yeah, this is not very surprising. So I have a specific example where weights are 1, 1, 2. F and f prime are homogeneous degree 3 polynomials. And we have an isomorphism between the varieties given by f and f prime, which fixes the origin. But the weighted blowups of the varieties given by f and f prime, they are not equivalent. So yes, this is not surprising, because if you change your embedding and keep the weights the same, a different monomial or polynomial might correspond to some combination of the weights. So yeah, it's easy to find some examples more. So now I'll state the theorem of Kawakita that I use, that is essential for constructing these divisorial contractions to CA endpoints. So for me, for simplicity, I'll take n at least 3 and let x have terminal singularities with a CAN singularity at P. Let phi be a birational morphism whose center is P. Then phi is a divisorial contraction if and only if it is locally analytically equivalent to a weighted blowup of this local analytic form of a CIN singularity. And this weighted blowup, the possible weights are described, and they satisfy some certain combinatorial conditions. So it's not too important what these conditions are right now. Maybe the last one, that the weight of H is R1 plus R2. And we can also check that the weight of this term, x1, x2, is R1 plus R2. So in fact, the weight of the whole polynomial or power series is R1 plus R2. So Kawakitas' description was local analytic, and I'll describe an algebraic definition or way. So let's fix these n at least 3, R1, R2, and A, as in Kawakitas' theorem. Let f be a polynomial or a convergent power series such that its weight is R1 plus R2, just like in Kawakitas' theorem, and that f defines an isolated CAN singularity at the origin. Then the weighted blowup with these Kawakita weights of the variety defined by f, or not the variety, but the complex analytic space defined by f, is exactly this Kawakita blowup. So I say Kawakita blowup, I mean a weighted blowup that is local analytically the R1, R2, A1 blowup of such local analytic form. So this means that to see whether a weighted blowup is this Kawakita blowup, we don't in fact need to do this whole analytic coordinate change. We can just do enough so that the weight of the polynomial is correct, and then we know that our morphism is a divisorial contraction or Kawakita blowup. And one more thing is that if the weight of f, so if f prime is another polynomial or power series with the same weight, and if f and f prime define an isomorphic singularity at the origin, then the weighted blowups are local analytically equivalent. So this means that just these weights, n, these positive numbers, n, R1, R2, A, define the type of the blowup locally analytically. Yeah. So I'm not sure if I have not found this result anywhere in literature, but I wouldn't be too surprised if it is known in some circles. The proof of this uses the following lemma. So let x inside Cn and x prime inside Cm, let these have weights w and w prime. Then their weighted blowups are analytically equivalent if there is a weight respecting biholomorphism which fixes the origin. And by weight respecting, I mean that if we write psi in its coordinate functions and its inverse as coordinate functions with theta 1 to theta n, then just the weight of psi j is at least the weight of the corresponding variable, so at least the weight of wj prime. And the weight of theta I is at least the weight wi. So to me, this seems like a very fundamental lemma when working with weighted blowups, but I have not found this in the literature. So I'll say one note that there can be two blowups that are local analytically the same, but algebraically they're not the same. So this means even though there is only one local analytic type for a Kawakita blowup, there can be multiple algebraic types. So for example, to prove that a variety is birationally rigid or birationally birigid, or to compute the pliability, we really need to consider all of these algebraic blowups that can be more than one corresponding to one analytic type, or corresponding to one choice of weights of the blowup. So now we can start talking about how to construct these divisorial contractions globally. So I'll do so this algorithm works in general, but to make it simpler, I'll look at an example of a sextic double solid with a CA4 singularity. Without loss of generality, we can assume that this CA4 point is at px, so has coordinates 1, 0, 0, 0, 0 inside the weighted projective space P 1, 1, 1, 1, 3. So this equation that I've given is just weighted homogeneous degree 6. So it's a sextic double solid. And I'll denote the variety, the sextic double solid, by x hat. So this hat is just notation. And I will choose the weights. R1, R2, A1 is 3, 2, 1, 1. So what we can do is we start from our sextic double solid. We look at the affine patch where x is non-zero. So this is inside C4. And then we have a local analytic map to this local analytic form of this CA4 singularity. And then by Kawakitas theorem, the 3, 2, 1, 1 blowup of this x1, x2 plus h is an analytic germ of a divisorial contraction. So now we have the divisorial contraction locally analytically, and we'll try to make it better. So we'll try to make it algebraic. So this map in this case is w goes to minus t plus w minus some homogeneous degree 2 polynomial in yzt minus homogeneous degree 3 polynomial in yzt and some other higher order terms. It also t goes to t plus w plus homogeneous degree 2 polynomial in yzt and some higher order terms. So this the weight w is the one with weight 3. So now what we'll do, since this is an infinite power series, what we'll do is truncate it. So we truncate it, see, at this position, and the upper one at this position. So we're left with t goes to t, and w goes to minus t plus w minus a2, which is now just a homogeneous polynomial in y and z. So we get a local morphism, algebraic morphism. We can do a bit better. So this is just a local morphism, so we homogenize with X to get a global morphism, an isomorphism. So we globalize, we just multiply with a high enough power of X to make everything homogeneous of degree 3. So we get an isomorphism from X hat to X bar, and now we can check that this X bar on the affine space, on the affine subset where X is non-zero, this is given by a polynomial whose weight is 5 with respect to these weights 3, 2, 1, 1. So by the proposition I had, the 3, 2, 1, 1 blow-up of this variety given by F lock is a divisorial contraction. So we've constructed this divisorial contraction algebraically. So yeah, this is algorithmic. So when I say algorithmic, I mean, so first this works for any weights R1, R2, A1. It's not really specific to Sextic double solids. It can be used for other varieties. This local analytic coordinate change, I have described this, what it looks like. So this infinite power series, I've given formulas how to compute these and made a computer program to compute this. I've described where to truncate it depending on the weights. And then after you globalize it, you get a global divisorial contraction. So this is an algorithm to construct divisorial contractions to CA endpoints. So now that we have this, so on this last step, we saw we got the divisorial contraction, but it was still, it didn't have a very nice global form. So I'll give it a nicer global form by embedding this into a toric variety. So I define a toric variety T, which is the affine 6 space. I take away the vanishing of x, y, z, t, and take a C star quotient, where the action is given by this matrix. So the top row of the matrix, we see the weights of the weighted projective space that the Sextic double solid lives inside P11113. And on the top row, we see these weights 1132. These are the weights of the blow-up. And then it has a natural map, this toric variety, to the space P11113. So this is the natural map, sending, which is basically, this map is U, X, etc. Sending this to X, U, Y, because U times Y has degree 0 in terms of the second by degree. So it has a natural map here. And using this description for T, since it's a toric variety, we can look at its Mori chambers here. So I'll remind that we constructed the divisorial contraction. So in this case, it is a restriction of a toric divisorial, a toric morphism. So this y bar, it's a proper transform, strict transform of x bar. And the restriction is exactly the same morphism, the divisorial contraction we constructed on the previous slide. So now to construct a Sarkisov link, we would need to continue with this. So the first step is a divisorial contraction, and then we can see what we have next. So if I write down the diagram for the secondary Fano, you see that we have variables u 0 minus 1, x is 1 0, y, z, and w lie on 1 1, and t is 1 2. And our ample model is given by, let's say, 2 1 here. So here, yeah, there's not much to do next. The next, since it's a two-ray game, there's only one map we can have next, which is, yeah, the toric map restricts to a morphism which contracts 10 curves. So this one here. So we see that that's not part of a Sarkisov link. So a Sarkisov link should end with either a divisorial contraction or a fibration, which this is neither. So the toric two-ray game, which we have, it does not restrict to a two-ray game of y bar. So there are some techniques to solve this, which is unprojection. So I put dashes here because for me, this is just changing coordinates or changing the ideal, embedding our variety in a different ambient space. So in this case, we introduce a new variable xi here. So yeah, this is the new variable. And now this unprojection gives us an embedding of our x hat to a variety, which I now call x. Now the ambient space for x is given by the weights here. So 1 1 1 1 3 5. The divisorial contraction is still the same. And yeah, now we can run the two-ray game, and we see that the toric two-ray game restricts to a Sarkisov link for x. So we'll have a divisorial contraction, a flop. This flop here is local analytically. It is 10 Atiyah flops. In general, we can have, for other CAN values, we would have different amounts of flops, or maybe no flops, or maybe some flips. And the last morphism is a divisorial contraction to a cyclic quotient point. It's Kawamata blowup, not Kawakita. And this way, we recover Sarkisov link found by Okada. So this construction, starting from a CA4 point, is very different. So we have to work really hard to get this first divisorial contraction. But for cyclic quotient points, these come a bit more naturally. So I'll comment on what happens for lower values of n. So I tried the same approach for n equals 1, 2, and 3. but these never gave me a Sarkisov link to something new. So it was always either a self-link or a bad link, meaning that the Sarkisov link is almost, the link is almost a Sarkisov link, but the last step is not a divisorial contraction, but it contracts k-trivial curves. So it leaves the Mori category. So I'll give an overview of the lower values. So as we saw before, a smooth sextic double solid is super rigid. With ordinary double points, if it's Q-factorial, it's super rigid. With CA1, CA2, CA3, we do not know. We expect super rigid for CA1 singularities and CA2 singularities if the singularities are general in some sense. For CA3, we don't have any more super rigidity because I constructed a Sarkisov self-link. And for CA4 up to CA8, as we know, this is birationally non-rigid. And one family, CA7-3, this had a link to a Del Pezzo vibration, so this is non-solid. Yeah, constructing these Sarkisov links, often I need to do lots of these unprojection changes, so I'll get many. So this variety upstairs can be given by many generators, either after the first divisorial contraction or somewhere later, can be given by, let's say, 6 or 8 generators in the ambient space. It's not always very easy, but it's doable. Okay. Yeah, so these question marks, yeah, it would be interesting to see what's going on there. Okay, thank you, everyone.